Today, large language models are rapidly transitioning from simple query response engines to systems that execute fully autonomous workflows. But when you try to scale an agent's runtime from 20 minutes to 6 hours, the system breaks. If you rely on a traditional single-prompt architecture, the failure rate for long-horizon tasks is near absolute. Extended runs trigger 3 predictable failure modes. First, context rot degrades the model's logic. Second, session amnesia wipes its working memory. And third, the model is structurally incapable of objectively evaluating its own output. To see this shift in action, look at this structural comparison. The left shows a single linear node looping into itself. This is how most people build agents today, and it fails. To achieve multi-hour autonomy, we have to abandon the idea of a self-correcting model. Instead, we use the architecture on the right, a tripartite adversarial network operating across strictly isolated context windows. We are going to deconstruct the specific node architecture engineered by Anthropic to push agent runtimes past the 6-hour mark. Achieving this level of autonomy requires a different discipline. It is a shift away from stringing together clever prompts towards rigorous systems engineering. This diagram represents a standard LLM session taking in data. As the agent gets deeper into a long run, we measure a degradation in logic, known as context rot. Nearing capacity, the model experiences context anxiety, rushing to finish tasks. To circumvent this, developers often use engineering patterns like the Ralph loop. This is a deterministic while loop that takes command line outputs and feeds them directly back into the exact same model session. The critical flaw is it never wipes the slate clean. Keeping every task in the same memory space compounds the rot rather than solving it. Relying on a single context window for both active execution and working memory guarantees a systemic collapse in any long-horizon build. The next structural hurdle is what we call the self-evaluation trap. Large language models are biased towards sycophancy. If you ask an LLM to review its own generated code, it will inherently rubber-stamp the output and approve its own work. To break this bias, we adapt the generative adversarial network framework for agent scaffolding. We split the base LLM into 2 distinct nodes, a generator and an evaluator, separated by a rigid boundary. That boundary represents isolated context windows. The builder and the critic must operate in entirely separate spaces, with 0 shared memory. When we divide the labor this way, the engineering problem becomes highly tractable. It is incredibly effective to take an isolated LLM, give it a strict grading rubric, and tune it to be a harsh, objective critic. Conversely, trying to tune a single LLM to be simultaneously self-critical while it actively generates complex code creates a massive cognitive bottleneck. The model simply cannot hold both roles effectively. Reliable quality assurance in autonomous workflows requires objective adversarial pressure. To prevent amnesia, we move state management from internal memory down to the file system. Agents write their state to JSON files to avoid overwriting. This enables contract negotiation, iterating through the file system until both nodes agree on exact criteria. Once the build starts, the evaluator ignores the vague initial user prompt. It uses tools like Playwright or Puppeteer to run live tests strictly against that negotiated JSON contract. This specific adversarial loop proved its worth during a 6-hour autonomous build of a retro game engine. Because the evaluator was actually using the application, it caught deep production bugs like fast API route ordering that a standard loop would have easily missed. It enables an ultimate failsafe. If the codebase becomes too tangled, the evaluator forces a total project wipe and restarts from scratch. A single agent loop refuses to execute this maneuver. By externalizing state to disk and forcing a rigorous pre-build contract, we completely insulate the autonomous agent from both context rot and its own sycophancy. This diagram shows the final architectural node. It drops in at the very top of the hierarchy, the planner, responsible for translation and scope. Its operational scope is strictly limited. The planner takes a vague, high-level user prompt and decomposes it into broad macro sprints. We enforce a strict complexity budget here. The planner is explicitly forbidden from defining granular technical specifications or low-level architecture. If the planner dictates low-level logic early in the session and makes a mistake, that error will cascade, it will magnify, and completely corrupt the run. Keeping the initial specification high-level forces the generator and evaluator to solve the actual implementation details dynamically, relying on their real-time feedback and live testing. The planner acts as a high-level product manager. It prevents long-horizon project drift without attempting to micromanage the deterministic build process. This tri-node architecture maps directly against the evolution of frontier models, specifically tracking the leap from Claude Opus 3.5 to Opus 4.6. As base models advance, the harness evolves with them. The introduction of 1 million token context windows begins to absorb and outdate earlier scaffolding requirements. The explicit step of sprint decomposition becomes redundant. The base model's internal planning coherence and context tracking naturally improve, allowing it to hold a complex build without being force-fed tasks. However, the core structural requirements do not disappear. Despite massive context windows, adversarial evaluation and file system state management remain critical to achieving subjective quality and true functional autonomy. Modern system design requires moving beyond prompt-based patches for structural limitations. Build the environment, strictly define the contracts, and let the adversarial process drive the execution.